Let's talk about differential equations then. So, what is a differential equation? Why do we want to know them for this class? That's the big question. In a nutshell, a differential equation is really just an equation, so it's got an equal sign in there, but it's specifically an equation that relates the derivative or multiple derivatives of a function back to the function itself. So these equations, you'll often see notation for derivatives flying around in them. And you definitely want to recognize that the unknown in this equation, the thing that we're actually solving for, is that unknown function. Now, in my little intro that I have here for differential equations, I'm using y as my function, but I tend to be pretty loose with this, and your professors probably will as well. You can call this u, you can call it p. The name of the function isn't necessarily important. Also be aware that the notation that we use for derivatives could be different from person to person. You know, you may be looking for information on one website, they might be using this prime notation for derivatives. Some other site is going to use like the Leibniz notation. That's okay. Again, the key fact for what makes a differential equation is that we're taking some sort of function, putting it into an equation, and it's related back to its derivative or higher derivatives in some sort of way. So I just completely made this up off the top of my head. I have some unknown function u. It's equal to 3 plus the second derivative of that same function. There we go. That is a differential equation. I'm going to play around with this. I'm going to use some alternate notation here. I'm going to say du dt. No, I don't want du dt. We'll get there. I'm going to say u is equal to 3 plus, and then I'll use d squared u over dt squared. That happens to be the exact same differential equation, but notice how I'm just changing the notation a bit. I'm using the Leibniz notation for derivatives rather than the prime notation. All right, other big thing about these differential equations. You're probably used to solving equations in algebra, probably other classes. It's a pretty common thing to do. The important thing to remember here is that what you're solving for is a function. So it's a little bit more of a complicated or bigger entity than just a single number. That's why the techniques are a little bit more involved, and it really matters the type of differential equation that you're starting with. Other quick examples of differential equations I have listed out here. So this one, the unknown function is y. We can see that its first derivative is equal to the original function plus 2 times sine of t. I think the other one here, yep, that's another one. We have the third derivative minus 2 times the second derivative minus x is equal to 2 times e raised to the power of that original function. So everywhere I see that y, I'm thinking of it as a function. The x, or the t in this case, that just happens to be the independent variable, the input of the function itself. All right, other, I guess, vocabulary that we want to know about differential equations. It's very common to classify a differential equation by the highest derivative that you see in that differential equation. So running around here, let's go back up to these examples. This first one, the highest power is right there at the front. It's, it's a first derivative. There it is. So I'd simply classify this as first order. The other one has, let's see, its highest derivative is a third derivative. So we'd simply classify that as a third order. Pretty straightforward, you know, look at whatever derivatives you have flying around in there, find the biggest one. That's going to be the order of the differential equation. That's a kind of what do I want to say, a coarse way to start organizing these things, but you can get even more specific. So now we can get into what are known as linear differential equations. In a linear differential equation, the highest power on our original, or the highest order for derivative is really just going to be its first power. And these have a very specific form that they can be written in. So you can write them with their first derivative, maybe some sort of function multiplied by the original, and then you might have it equal to some sort of function on the other side. You'll see this form show up one more time when we really start diving into the linear differential equations. But again, some common things that you're looking at here is that they are first order. All right, what else do we want to say about these? In a nonlinear differential equation, you'll see that you may have your original function there, but they are not necessarily raised to just the first power. They could be divided. They could be that'd be like to some sort of negative power, and they can't be written in that very specific form. Let's dive into that one a little bit more. So this one is a wonderful example of a nonlinear differential equation. And I'll definitely call this nonlinear because notice how, well, first of all, you have that second, what is it? Let's see. I want to point out the problem areas. One problem area is here I have a second derivative, but it's inside of a sine function. That's a bit of a problem. We're not necessarily just raising it to a power. That's an issue. Here I have a first derivative, but it's being divided. So that's like raising it to the power of -1. That's an issue. Here's another issue where I'm taking the original function and I'm squaring it. So it's those things that make it nonlinear. In a linear one, these are in some ways a very nice type of differential equation. If I have derivatives running around there, if I have the original function, nothing's raised to a power other than just a single power, a power of 1. Let's see, other things that we can use to classify this. Some differential equations are called homogeneous and some are called inhomogeneous. This has really to deal with that term at the other end of the equal sign if it's written in this nice standard form. And it's all down to whether that particular function is equal to 0 or whether it is not equal to 0. Notice that specific term, the one that I've labeled out as q, it's not associated with the original function or the derivatives of the function. It's the function, if it's a function of anything, it's only a function of the independent variable. So if it's equal to 0, bam, we're done. We can call that a homogeneous differential equation. If it's not equal to 0, then it's an inhomogeneous differential equation. The examples, they're very subtle, so I'm going to try and point out exactly what I'm looking at here. So here I have a differential equation. We could classify this as a second order differential equation. You know, it's got a second, a second derivative in there, so second order. But all of the terms that are involved in here, they all involve the original function, 2y t squared by a y prime, then I have a y double prime. So they're the one function that is only a function of t, only a function of the independent variable, it's 0 and it's sitting there on the right side of the equal sign. That 0 is what makes this homogeneous. All right. Now carefully compare this with the other example and see why this is not homogeneous. So almost all the terms are the same, right? It's got this 2y, it's got the t squared y prime, it's got the y double prime. Those things are matching up, but there is a piece that does not involve y. And it's this guy right here, the -5. So in this case, that would be our function q of t. And since it's a 5, since that is not equal to 0, that's what makes this an inhomogeneous differential equation. All right, those are some just basic classifying things. And one differential equation, I've already kind of hinted to it, could have multiple labels attached to it. So you really want to perk your ears up when you start hearing these labels and saying, all right, that specific word means something, and that specific word means something, so that by the time you describe the entire differential equation, you actually get a lot of information as to what it looks like, or the different pieces that are in it. Let's take a look at really just classifying a bunch of these, and I think you'll get a much better sense of what I'm talking about. All right, so this is going to be our first example here. And it's basically a table. I have lots of differential equations in that first column. And basically, we just want to classify these. We want to say what their order is. We want to say whether they're linear or nonlinear. And then we want to say, are they homogeneous or are they not homogeneous or inhomogeneous? So let's do the order first. It's usually one of the quickest things we can go through. Remember, you're always looking for the highest order of derivative. Right, so starting off with the first one here. It looks like u is the name of the function. T is the independent variable here. And the highest power is just a second derivative. So the order is 2. Nice and simple. If you're following along, Go and try this for yourself. What about the next one here? It's got a lot of different pieces in it. Think carefully. What is the name of the unknown function? What's the name of the independent variable? More importantly, what's the highest derivative that you can see in that differential equation? Take a guess, type it in the chat box right now. Make sure you're on the right track. Excellent. Yes, I'm seeing lots of 3s show up. It is indeed a third order differential equation. Looks like I also have a question in the chat box. And this is specifically talking about linear versus nonlinear. This one says, when it comes to a linear differential equation, does that mean it only has the first derivative in it? The answer is no. It could actually have like the fourth derivative, third derivative. What really makes it linear is that the original function or the derivatives of that original function, they're only raised to the power of 1. Actually, maybe I could clarify that a little bit with this example here. Here we are. So notice how in this example here that I'm dealing with, we do have stuff like the second derivative. So it's not uncommon to have even third or fourth derivatives. That's not necessarily what makes it linear. But I want you to notice something. So here I have the original function. It's essentially being raised to the power of 1. There's no other higher powers on it. This guy is being raised to the power of 1. Again, no other higher powers on it. And here's my last derivative. It's also raised to the power of 1, essentially. That's really what's making this linear. If I wanted to break this, if I wanted to make it nonlinear, then I could do a couple of things. I could take one of these and raise it to a higher power or even a negative power. That'd no longer be linear. Or I guess another way is if it ended up on the bottom of a fraction, that'd be like raising it to a negative exponent. That would not be linear as well. Let's see, other quick questions. Are homogeneous and inhomogeneous, are those different forms of linear differential equations? Something could be linear and, what is it? Let's see, how should I say this? It really just has to deal with the forcing term on the end. The function that is not involved with the original function, if that is 0, then it's homogeneous. And if it's not 0, then we say it's inhomogeneous. Again, don't necessarily think of connecting it with linear or nonlinear. You could have nonlinear homogeneous equations and you can have linear homogeneous equations. We're all just kind of packaging all kinds of different things together. All right, I think that's takes care of those questions. Let's see if we can go ahead and continue down this column. All right, again, we're tacking the order of these. We're looking for the highest power. Everyone did an excellent job on finding the third derivative in this one. So moving on further, this one, its highest derivative is a second derivative. So we'd say that's a second order. This one, you'll notice that they actually have a fourth derivative on there. That's why it's in parentheses. So this is a fourth order. Then at the very end, looks like it is a single derivative. So we will say that that is first order. So always looking for that highest power. That's where we get the name for the order. All right, moving on. Now we need to determine linear versus nonlinear. This is where it starts to get a little bit trickier. So as you're combing these over, here's what you want to do. You want to look at the function, the unknown function, or its derivatives, and see if it's raised to any powers. Is it possibly being raised to any negative exponents? Is it being multiplied by another version of the original function? Those are things that would make it nonlinear. If every instance you see is just a power of 1, then we will call it linear. All right, let's start off with the first one. So yep, there's our unknown first derivative. I don't see any powers on it, so that's good. Here's an unknown second derivative. Again, no powers or anything on it. So we will call this one linear. Right, just as before, I'm going to let you think about the second one. Do you think this one is linear or do you think it's nonlinear? Comb it over real quick and go ahead and put your guess in the chat box. Excellent. This one is definitely tricky, but it is nonlinear. And the reason why it's nonlinear is because we have a little bit of an issue with the original function being multiplied by the first derivative. And we really only want to see like our unknown function raised to a power. It might be multiplied by some function of t, but we don't want it multiplied by a version of itself of the same u. Very nice. Moving on, let's see what else we got. Oh, that's a bit of a problem. Look at that right there. They have the second derivative raised to the third power. We know what to call that one. We will call that one nonlinear. Let's see, fourth example. There was a question that says, why would we call this one an order of 4 instead of an order of 0? It has specifically to do with that 4. That means the fourth derivative. So that's why it's called the fourth order. Right now, though, we have to figure out, is it linear or is it nonlinear? What do you guys think? Linear or nonlinear for this one? Not bad. I see a few people kind of going back and forth. This one is indeed linear. All right, so let's carefully point out the pieces. What do we got going on here? So here I have my first version of u, that unknown function. It's being divided by a constant. No problems with that. Then I have just the number 5, minus 5. It doesn't involve u whatsoever, so nothing really to worry about that, or anything to worry about the 5t. I'm only looking for pieces of that unknown function. So here's where the fourth derivative is, but that is a fourth derivative. It's not being raised to the fourth power. And it's the notation is very tricky. Like, it almost looks like it's being raised to the power of 4, but there is a difference. If you see something like an unknown function with the number in parentheses, like right next to the name of the function between the independent variable, that is definitely a derivative. If I was trying to really make sure that this was a power, you know, I wanted to raise the function to the 5th power, then I'd probably put a pair of brackets on it and really make it kind of clear that this, whoops, that's not a derivative, that this 5 would be a power. All right, I think we have one more of these. The last one also happens to be linear. Yep, that's because all versions of u are just raised to the power of 1. All right, one more column to go. Now we need to define whether these are homogeneous or inhomogeneous. And this all has to deal with if there's a piece in here that doesn't involve the unknown function, is it 0 or is it not 0? All right, first one, that involves u, but look, we have a piece that does not involve u, so this is what I'd usually just call the Q function, and sure enough, it's not 0, so we would say that this one is inhomogeneous. All right, next one. Now it's time for you to give this a try. Is there any piece of this differential equation that does not involve the u? And if you can find one, is it 0? Is it not 0? What's going on there? What do you think? You guys are on your game today, I can tell. So yes, you are correct. This is homogeneous. I guess a good way to tell is if you comb over this one, everything involves the unknown function u in some sort of way. So if there is a piece that doesn't involve u, it has to be 0. It's essentially not in there. Moving on, let's see what else we got. So I see that there's this piece on the end. It doesn't involve u. So is this one inhomogeneous? Not quite, not quite. Well, why not? Because it's got another one on the other side. Someone did a little bit of work with this. They essentially just didn't simplify it. We could go ahead and easily subtract 1 from both sides, and then it'd be gone entirely. In which case, all of the leftover pieces would only involve u. So actually, this one is homogeneous. And is a wonderful lesson to make sure you'll always simplify your equations so you can clearly see what pieces involve u and which ones don't involve u. All right, moving on. Let's see what we got here. So this piece has a u, this piece has a u, but there's definitely a lot of other pieces that do not involve the u in any way. There's no way that these are going to simplify and cancel. One has a t, one doesn't have a t. So I will definitely call this one inhomogeneous. All right, one more to go. What do we got for this one? So there's a u, there's another u. All of the pieces involve the u in some sort of way. So if there is another piece, like on the other side of the equal sign, this one does have another function. It's 0, homogeneous. Excellent. Now, all of these things are specific labels. So real quick, watch how you can actually put all of them together to describe essentially what you're dealing with when it comes to a differential equation. So this first differential equation, you can call it a second order linear inhomogeneous differential equation. It's a mouthful. I know all of those words are just kind of rolling off the tongue at first, but all of them mean something in terms of the highest power, what's happening to the unknown function, and whether there's any, and whether the function involving just the t is 0 or not. But you really put them all together to describe what's happening. Let's see, the second one, we would say that that is a third order nonlinear homogeneous differential equation. If you have to say these over and over again, you get much, much better at saying them, but notice how all of them contribute to describing it. All right, any other thoughts or questions before we get into a little bit of solution work? All right, just being able to describe these things and know what you're talking about is part of the battle, but of course we want to get closer and closer to actually solving these. But I threw in an example just to really emphasize that the thing you're looking for is a function. It's not a number. Most of the time it's not a number. It is an entire function that you're really trying to solve for. So in this one, we're not actually trying to solve it. I just have a function and we want to verify, show that it really is a solution to the following differential equation. By the way, for keeping score, this differential equation that I have written down, it happens to be a first order. It is a linear differential equation, and it is inhomogeneous. All right, so how do you tell if something is a solution or not? Well, essentially, if we plug it in, it should balance out. That's how you know you have a solution. Whether you're working in algebra or whether you're working in calculus, that's how you know you have a solution. So that's what we're going to do with this one. We're going to take our function, and we're going to try and sub it in to our differential equation and really just make sure that everything balances out. Now, since differential equations involve derivatives, we'll also have to plug in a derivative to this function as we're testing things out, okay? So let's see, here's our function. U of t is equal to cosine of t over t. And we need to do some really quick work. We need to figure out what its derivative is so we can also put that in there. All right, so let's see, how do we take the derivative of this? I think the quotient rule is going to work just fine. So low, derivative of the top, minus the top, and then the derivative of the bottom all over the bottom squared. All right, so that would be the derivative. So we need to plug that in for this u prime, and we'll plug the original one in for u. If everything works out good, if this really is a solution, then it should equal negative sine of t by the time we're all done. We're just verifying this. All right, let's do that. So t is going to be multiplied by the derivative. So we just did a little bit of work figuring out what this is. Plus, here's where I'm plugging in the original function. The original function was cosine of t over t. And if this is a solution, it should equal the negative sine of t. I'm going to put that little question mark over the equal sign because I don't know if these things are equal just yet. And it's my way of reminding myself not to bring things over that equal sign because I don't actually know if they're equal, but at least gives me a target. Cool. All right, let's do some simplifying, see what we can do. from there. Okay, so over on the left side there, I can see that I have a single t that will cancel out. So now we're just dealing with a minus t sine of t, minus cosine of t all over t, plus another cosine of t all over t. And that was pretty good for us. You know, if I'm looking at these, it looks like we have two fractions. We're putting those fractions together, and they happen to have a common denominator. So I can definitely put them together just by combining the numerators of each of these fractions. Which, as you can see, is especially handy. As soon as I put these two fractions into one, the minus cosine and the positive cosine, those are going to cancel each other out. Okay, so this is looking better and better. Oh, and there's just a little bit more simplifying left to do. So we still have a negative t sine of t. It's all being divided by t. So these last two t's are going to cancel out. And we're just left with a negative sine of t. So in comparing it to what we had on the other side, or what we wanted it to equal, we can see that yes, they are the same. So is this unknown function, is it really the solution to the differential equation? The answer is yes, because we can plug it in there and it satisfies it. Both the sides balance out. Okay, questions or thoughts so far then? Good to hear, good to hear. Okay, so we have different ways of describing them. We know if we're given something that might be a solution, how to test it. But I haven't talked at all on how we actually go about solving a differential equation. This depends largely on the type of differential equation that actually drops into your lap, but actually you do have some tools that you could start solving some of these right now. And when I say tools, I mean, just kind of digging into your bag of tricks from beginning calculus, you have some things that you can use to solve some of these differential equations. Let's take this first one here. The first thing I want you to do is see if you can classify this. In the chat box, type the order. Is it linear? Is it not linear? Is it homogeneous? What are we really dealing with? And then we'll get into the solving process. Looks like Emma's out of the gate already with a very strong guess. Very nice, very nice. Another guess is showing up in the chat box. Excellent, excellent. I would agree. This is definitely first order. We're only dealing with the first derivative. It's linear because anything that involves u is really only raised to the first power. And yeah, it's definitely inhomogeneous. Look at all that stuff on the right side. None of that stuff involves u. And it's definitely not zero. There's a ton of stuff over there. So inhomogeneous. So actually, we can go ahead and solve this particular differential equation. And we can solve it because if I'm trying to work my way back to the original function, then we can already do an antiderivative. So all of this stuff involves a derivative. I'm just going to do an antiderivative, and we'll be able to get to the original function just fine. Now, it's interesting, this one you'll notice also has something else. In addition to the differential equation, we're given a little bit of information about the function. We know that when t is equal to 0, that's this little inside piece here, when t is equal to 0, that the entire function is going to equal 4. We call this a little initial bit of information or this additional bit of information, we call this an initial value. So when you have the differential equation with an initial value, sometimes we call the entire thing collectively an initial value problem. Either way, we still want to solve it. So we'll end up finding out what the mystery function is, and then we'll use this initial value to find any unknown constants that might be lurking on the inside there. All right. So let's see. How are we going to roll back to the original function? Well, the fundamental theorem of calculus is going to really help us in that process. If I take the antiderivative of a derivative, this is where I'm hoping back to get to the original function, or at least a family of functions that will satisfy the differential equation. You'll notice that I put that plus c on there. That's where the initial value is going to play a part. It's going to help us figure out what that c is. Okay, so yeah, let's see what we got. So we're going to take the antiderivative of e to the t plus cosine of t plus 2. And then really just take this thing term by term. So antiderivative of e to the t, that's e to the t. Antiderivative of cosine, so this comes from sine. And antiderivative of 2, 2t. And then we'll put our little mystery constant on the end there. So our mystery function u is equal to this. So we have a solution, and now we can use the initial value. So at 0, if t is equal to 0, this entire thing should equal 4. So I need it to equal 4. And let's go ahead and drop in a whole bunch of zeros for every single one of those t's. So really, the only thing we don't know in this differential equation is that unknown constant on the end. We'll do some simplifying. We'll combine what we can. We'll solve for that c and see what we have. E of 0 goes to 1. Sine of 0, that goes to 0. And yeah, 2 times 0, that goes to 0. So 4 equals 1 plus c. So I know that the value of c is 3. All right, so now we can actually write down our entire solution. You can write this as u of t, or you can just say it's u, either way. The important part is all of these other terms that are involved here. Let's see, we said c was 3, c was 3, so there it is. So this entire function, the entire thing, is the solution to the differential equation, or you could say that this is the solution to the initial value problem. Now keep in mind, we were able to solve this one because the special form that this one was in was basically the first derivative was equal to some sort of function that did not involve u. So if you're keeping track, we have a form right now. This is a first derivative equal to some other function not involving u. How do we solve those? You just take an antiderivative. That's your solution. All right, thoughts or questions before we pick up some other techniques? Good question. This question says, how come we dropped the plus c from the antiderivative of the derivative of u? We didn't necessarily drop it. Let's go ahead and keep track of where it is. So here you're seeing where I'm actually taking the antiderivative of u prime, and the c shows up right on the end. So I haven't forgotten about it. It's right there. Now, it may look like it disappears, but that's because I'm using this initial value. I'm using that in my function for u to go ahead and solve for c. So at this point, now we're actually solving for c. Yep. So I go through a little bit of work. I've plugged in all of my stuff. Here's where I actually figure out the value. And once you know its value, then you can go ahead and tack it on the end as an actual number. So c is really still there, but now we know what it is. Does that help out?